So I think you'll see that this presentation follows quite neatly on from the Pont Bren example presentation, and we'll be returning to some of the themes that we learned about in the early sessions this morning. Very much a focus on the relationship between water and soil. So I'm Chris Stoate. I'm head of research at the Allerton project, which is a research and demonstration farm in Leicestershire. The farm itself is outlined in the purple area on this slide, but we're working, it does just about work, just at this area here, but we're working at the landscape scale, and in particular in the headwaters of these two tributaries of the river Welland, which flows out into the Wash. So a little bit about the farm itself and the research work we've been doing at the farm scale before I move on to the landscape and the catchment scale. The farm business at Loddington has a rotation of wheat, rape, wheat and beans or oats. It's a joint enterprise with a neighbouring arable farm. We now did have our own sheep flock, but we now let the pasture to a neighbouring sheep farm, and we do some contract work on other farms as well. So it's very much a farm business, but then we incorporate our research work into that and then demonstrate the results of that research and our practical experience on the farm to farmers who come to visit us from across the country. So if you want to come and visit us, you're very welcome. Get in touch and we can arrange something. So we've been going a long time, since 1992. I've been with the project right from the start. And the initial work that we were doing was on farmland ecology, including songbird conservation, crop pest predators and pollinators. We've been working on that. And the development of many of the environmental stewardship scheme options is now widely adopted across the country. So we were it was our bread and butter in terms of our research in those early days. But for more than a decade now, we've been doing much more work on soil management, including reduced tillage, looking at the effect of cultivation direction on runoff, and looking at the potential of infield barriers, specifically beetle banks for reducing runoff, and also management of tramlines. Outside the cropped area, we've been looking at the role of constructed wetlands for reducing the impact of our farming operations on water quality and ecology. And we've not been forgetting the domestic impacts, contributions of phosphorus to water as well. So this is an example of one of our erosion plot experiments, DEFRA-funded one. In this case, looking at comparing reduced tillage with a plough-based approach, looking at the effect of cultivation direction and the effect of a beetle bank running across the slope. And all of these have a benefit in terms of improving the soil for cropping and reducing runoff. So the reducing soil disturbance, reducing tillage, as we've heard this morning, improves soil structure, improves soil ecology, improves soil function, and has benefits for the crop and for water quality as well. So there's some real win-wins here. But what this project identified in particular was the role of tramlines as a pathway for water and associated sediment and nutrients to leave the field. And so another project that we ran at Loddington was looking at how we manage tramlines better, and effectively, to cut a long story short, using low ground pressure tyres, reducing the amount of soil compaction that is created in the first place, reduces runoff and improves infiltration. So that's the sort of message we can take forward to farmers, both locally and nationally. So just to summarise some of those results, tillage certainly has an effect both on the performance of the soil to support our crops and to reduce the movement of soil and nutrients to water. And low soil disturbance, reduced tillage is increasing earthworm numbers and soil microbial biomass, which are having a benefit the sort of events I've just been mentioning. And microbial biomass in particular, actually, this is the first study through a PhD project that showed that increasing microbial biomass within an arable soil can reduce the sediment concentration, the sediment load in both surface runoff and in subsurface flow. So, as we heard this morning, great benefits from enhancing soil ecology for our cropping, great benefits for water quality as well. Beetle banks, they do have a role in terms of reducing runoff, but and of course they have a benefit for the cropping in terms of enhancing the numbers of beneficial predatory insects, controlling aphids and other crop pests. But putting those across along contours is not always a practical option in fields that slope in all directions. We did also look at constructed wetlands. The message here was that they work very well on sand and silt soils, but rather less well on clay soils where you have very fine particulate matter that's held in suspension and travels right through the wetlands during storm events. But we've carried a lot of research on those. At Loddington, we have, as you've seen, a lot of the research has been on the erosion plot, or field scale, field corner scale. We also have a 155 hectare catchment that that was defined originally for a DEFRA-funded project looking at the relationship between land use and water, part of a national study. But since then, we've been developing it as a demonstration of ecosystem services, but without using the language of ecosystem services. So in other words, we're developing as a practical example of how an area of lowland England works. That's fairly typical of other parts of lowland England, in that it has arable land and pasture. Some of that pasture is grazed by horses, just as it is around Oxford. And some of the pasture is grazed by a productive sheep flock. We have environmental stewardship habitats on the arable area and indeed on some of the pasture. We have ancient semi-natural woodland at the head of the catchment, rural roads and houses, so really sort of microcosm of lowland England, and a great opportunity and a manageable scale in which to gather data to enable us to understand some of the processes that are going on within this sort of agricultural area. So we've been going a long time, since '92, as I said, and we've been able to gather data for some of these over that whole period. Others have come from the DEFRA-funded project that I mentioned, and others through postgraduate PhD or master's students that I co-supervise with universities across the country. So for this little area, we're gathering a lot of data on the whole range of things, not just those related to soil, those related to water, but on pollinators and beneficial insects and a whole range of things, and of course the economics of the farming system and the performance of the farming system as well. Now, because it's a catchment, we're able to gather data on water quality. And of course, the traditional approach here is to gather water at the base of the catchment, at some point along that catchment, analyze the water, quantify the amount of pollutant, whether it's suspended sediment or it's phosphate or it's nitrate or whatever it is, and we can use those figures to say, to understand and express all the bad things that we as farmers are doing to water. And we're failing to help the government reach Water Framework Directive targets, and it's all very bad news. But I think we can take a much more positive approach to this. We can use those same numbers, the water quality data, the nutrients, and indeed the invertebrates living in these streams, as an indicator of how we can improve the management and use of the natural resources within that catchment, within the land that's draining into that stream. So we as land managers can use those data to improve our resource use and management within the area that we're farming. So here's an example, some data not gathered from the base of the catchment. I'll show you some base of catchment for our landscape project in just a minute. But these are data gathered at a number of points along the stream within the catchment. So the sampling points are numbered 1 to 6. I hope you can see those on the map on the right. And the graph shows the red bars are that's turbidity, which is correlated with suspended sediment, which in turn is correlated with the total phosphorus concentration. And these are data from storm events, okay? So this is winter storm events. And you see that as we move down the catchment and see a greater influence of arable land use, we're seeing higher concentrations of sediment and higher concentrations of total phosphorus. So very low at the top of the catchment where the water's leaving the ancient semi-natural woodland, sort of moderate as it moves through pasture, and then getting much higher towards the base of the catchment as we move through the arable area. The blue dots represent soluble reactive phosphorus at base flow. And what we see here again is very low values in the top end of the catchment, increasing slightly at 0.4 and increasing dramatically at 0.5. And this is a result of contributions from domestic septic tanks. So we as farmers are identified as making a big contribution to phosphorus concentrations in watercourses across the country. And we have to accept that that is the case and we need to do something about it. But the fact is that the domestic sources are having an impact as well, and we need to understand that and accept that. So just an example of how by gathering a number of different data sets from this small area of land, we're able to understand some of the processes that are going on within it. And much of this boils down to the management of soil. And a number of points within the catchment, we have soil moisture sensors, which tell us how the moisture content is fluctuating throughout the soil profile. And this is one example of a wheat field from last year. No, this is the reverse of the graph you saw in the prompt presentation. So this time the rainfall's at the bottom of the graph, but it's the same principle. And you can see the lines there represent soil moisture, relative soil moisture at a number of depths. And you can see that between from December here to March, we're seeing saturation throughout the soil profile. And this is where we get runoff and erosion, loss of soil, impacts on water. Then at the soil surface, and 10-20 centimetre depth, we see a decline in soil moisture from the spring, from April, and then when we get to June, we start to see a decline at 40 centimetres depth, and then later on in June, we see a decline even at 60 centimetres depth. And this is the grain filling period, of course. So when soil moisture is going to be influencing the wheat yield. And so if we can improve our soil management, if we can get a better structured soil, if we can get higher organic matter, a better functioning soil, then we're going to be achieving better water quality, and we're going to be achieving better crop performance as well. And these are some data, just to give you a bit of an idea of sort of the data we have from the base of the catchment. Sediment load per day, just to illustrate that as stream depth increases in response to rainfall, then we see an increase in the sediment load. And so we know this. We see that the water turns brown when it rains, but this provides a graph to illustrate that. But still, what does it mean? Does it matter to us as farmers? Does it actually matter? Well, we can start to think, and we are only just starting to think, of this in monetary terms. We can start to think of the amount of money that's going down the drain from this little catchment. And this graph represents relatively low flows, so that the real storm events are not represented on this graph. So we're just starting to get an idea of that process. We've also looked at what's been going on in terms of soil biology across the three main land uses, arable, pasture and woodland, looking at the relative biomass of earthworms, microbial biomass, and soil organic carbon. And in each land use, you can see that they're lowest in arable land. This is perhaps no great surprise, especially given what we learnt earlier on this morning. But the aspiration must be, I think, to increase all of those within the arable area. Now, I'm not saying that we can get up to those values that you see in pasture or woodland for the organic matter, but we should be aiming to achieve that if we're to have a better structured soil, better functioning soil, and one that's going to have some benefits for our cropping, for our water, and I think for our biodiversity as well. So I want to move on to the landscape scale now, to a major project called the Water-Friendly Farming Project, which is based on 3 headwater catchments. The question we're asking is, to what extent can we move towards these Water Framework Directive targets by adopting a range of measures that are scientifically based and practically grounded? And a strong baseline is absolutely key to this evaluation. If we don't have a strong baseline, then we can't say how effective it was. So we have a period in which we're gathering baseline data, and we've in now a period in which we're introducing a whole range of measures, and then we'll continue to monitor them subsequently. What are we monitoring? Well, it's all listed there. And we're monitoring intensely at the base of each of those 3 headwater catchments. 2 treatment catchments, 1 control, so introducing the mitigation measures in those 2 treatment catchments, and the control catchment will remain unchanged. And then we're also doing some management at the landscape scale, 240 sampling points across the 3,000 hectare area. These are the sorts of results we get. This is for the total phosphorus concentration from the base of the catchment. It shows enormous fluctuation, largely seasonally. 2012, there's a lot of dilution from the rain, and in subsequent years you can see an increase in the late summer, early autumn period, which is before we're getting runoff, of course. So this is the impact from sewage treatment works in these catchments, phosphorus concentrations in water. And then later on in the winter, we're starting to see the added to the sewage treatment works impact, the contribution from sediment and phosphorus adsorbed to sediment particles. So a combined domestic and agricultural impact. And there again, for the suspended sediment, more specifically, fluctuating a lot, especially in that first year when there was a very heavy rainfall. And we reckon, a bit of a back of the envelope calculation this, but based on really good data, that we're losing around about half a tonne of soil per hectare per year from that area. The area has grass buffer strips within it. It's fairly well buffered within existing stewardship schemes. But what we've been doing is putting in constructed wetlands of various sorts, simple ditch dams, field drain interceptor ponds and floodwater ponds across the landscape. And for the larger ones, as you can see in that right-hand picture, planting them up with wildflower mixtures to benefit pollinating and other beneficial insects as well. But as I said earlier on, our research, intensive research at Loddington, has shown that while they can be very effective, and I've just shown a photograph of one that was, they tend not to be totally reliable on clay soils, and their efficacy does depend on the site in which they're located. And the crucial thing is, from a farming perspective, the crucial thing is that, of course, they don't keep soil in the field, which is where we need it to be. So is erosion control important? Well, yes, obviously it is. If we want to, we need to keep soil in the field, but as important, or perhaps more important than that, is the soil, the function of that soil within the field. We don't just need to keep it there, we need to ensure that it's working well, both to maintain water quality and to maintain crop production. So improving soil structure and ecology are key, and we're now starting to work with the farmers within these catchments to help them address this issue. And we're looking in more detail as well at the relationship between soil compaction, which again, there's the relationship between soil compaction and runoff risk, impact on water, but also on crop production as well. Because the sort of compaction that you can see in the photograph on the left there is not resulting in a well-performing crop. It's not high-yielding area of land, and it's also has very high runoff risk and is affecting water quality. So that's the sort of issue that we are currently addressing. And I'm having cards flashed at me. I've run over time, so I'll stop there. But if you want to keep abreast of the sort of research that we're doing at Loddington or at the landscape scale locally, then, well, come along, see what we're doing, or take a look at the blog. Thank you very much.